So this is the Process Dynamics and Controls Exam 1. Here's the work that was asked for the first problem. In this first problem, we are looking at a reactor with an exothermic reaction. With this exothermic reaction inside of the reactor, there's multiple things that are taken into consideration. First of all, with this type of oscillatory motion, the type of response that is normally projected is a critically or overdamped system, and in this problem this is not the case. This is due to there being a positive feedback between the two first order relationships of the material balance, which is given right here, which produces this Wi and it controls the concentration of the reaction, and this energy balance portion of the process in series, with the temperature being denoted right here. And with the exothermic reaction, when a certain amount of fluid / reactant is added to a reaction and the reaction is exothermic, heat is released, and with this heat being released, that causes the rate of reaction to also increase. And from that, there's a lower concentration of reactants that are available due to the reaction taking place. With that, there's a feedback between the temperature and the concentration that is seen within the reaction. And as the temperature begins to die off due to the adiabatic conditions of the reactor, the concentration then begins to rise due to the filling. And with the fall from the filling and the temperature decrease from the cool water, the reaction then begins to take place again, or more of the reaction begins to take place, hence the temperature rising, and this kind of motion goes back and forth until it settles out and reaches a new steady equilibrium point in temperature. Along with this positive feedback that's seen from the temperature within the reactor and the concentration, you can look at it mathematically as well to see why this is oscillatory. If we look at the roots that are found from the transfer function, we can find that the time constants for both roots are non-real complex roots. With that, one of them is positive and lies on the right-hand side of the plane, and due to this, we see an oscillatory motion inside of the reactor. Problem 2 asks us to look at and design a surge tank. And here's the work for this. We did this by solving for transfer function of a two area system surge tank with some wear resistance in between. And here's more work just for document sake. Sorry for the handwriting. So, along with this question, we were asked to sketch and explain how the surge tanks would vary with an impulse in the inlet flow rate of the tanks, and how that would affect the height of the overall vessel. So for the first height, you can see, which is a single tank, an impulse would cause a sudden rise in the height of the tank, but over time the pump, since operating at the same conditions, would then lower the height level, and there would be a slow decay of the impulse change or the height change from the large influx of fluid, which is then taken out by the pump over time. But notably, it would be decaying over time and slowly go back to an equilibrium. And in the surge tank, something similar would be seen, where the impulse in the flow rate would cause a height change in this first surge vessel. But over time, with the draining from the wear and the maintained height in the second vessel, the slow decay of overall height in the first area would come back to its original controlled height level. This varies from if there was a step inside of the tank, meaning that instead of a sudden impulse or a sudden change in the inlet flow rate, there is a change in the actual meter control for the flow rate, and due to that, there would be a new steady state equilibrium height, this denoted by this height nu right here. And this new height would be in response to the increased flow rate control setting from the inside, or from the inlet flow rate. For how this would affect the surge tank, the step change in the surge tank would cause an increase in the height in only this tank right here, which would limit the flow rates out of the tank right here, as well as mechanical malfeasances inside of the pump. If there was too large of a step, this could also cause overflow inside of the tank, and if this overflow were to occur, that would affect the overall height of this second area from the surge tank. Along with this, we were asked to design what we would suggest to be the best denotion for area inside of the surge tank, and if and when the surge tank is viable as a solution and can be used to limit the amount of change inside of the height of the tank. To do this, we would follow similar steps from the problem solving in this question, where we would use the transfer function's time constant from the surge tank, and with that time constant we can run an analysis on it by maximizing it. We can find the area inside of the tank that is necessary for the surge tank and where it would operate most efficiently. This was done right here, and it was found that the areas inside of the tank should be set to half to optimize the total flow rates inside of the tank, as well as the height differences between the two tanks. And to further optimize this, you can take the time constant from the normal tank that you want and the surge tank that you want, and find a ratio with them and take the limit. And when you do this, you find that as the ratio goes to infinity, the areas would go to 0, meaning that a larger tank area for area 1 would be beneficial if you wanted to limit the overflow and overshoot values from the height of the tank, as well as limit the overall equilibrium inside the tank. This has impacts on the amplification effects as well, meaning that the amplification effect seen from this change in the area of the tank would have either more drastic effects if you limited the size of the tank versus less drastic effects on the overall functionality of the system if you increase the size of the tank. So to conclude, I would recommend optimizing the area of the surge tank 1 if necessary to control the outlet parameters of flow rate that were necessary in this problem. Thank you.